In this video, we will talk about limits at infinity. For example, f of x equals 3x squared over x squared plus 1. Find the limit of f of x as x approaches positive infinity and negative infinity. Numerically, if you look at a table of values, it certainly appears that as the x values are increasing, the value of the function is getting closer and closer to 3. And as the x values are decreasing, the function seems to get closer and closer to 3 as well. In other words, it appears that as x approaches negative infinity, f of x approaches 3, and as x approaches positive infinity, f of x approaches 3. But let's take a look at the graph to see what's going on. Looking at the graph, the function does seem to approach 3 as the x values increase, and it seems to approach 3 as the x values decrease. So when that happens, this is called a horizontal asymptote. So the line y equals 3 would be a horizontal asymptote. So numerically and graphically, it appears that the limit as x approaches infinity or negative infinity is 3. But what we really would like to do is prove analytically that the limit is 3. So in order to do that, we're going to use some of the properties of limits that we learned back in Unit 1. The gist of this is that if you have a sum, a difference, a product, or a quotient, you can really go ahead and take the limit of each part separately. So keep that in mind as we go through this analysis, because we are able to basically take the limit of each term separately because of these properties. Great, so this should be pretty easy then, right? It seems like I can just take the limit as x approaches infinity of 3x squared and divide that by the limit as x approaches infinity of x squared plus 1. And I really could have even broken this up separately, and maybe I will just this once. So I could consider the limit as x approaches infinity of x squared plus the limit as x approaches infinity of 1. So this should work out great. He says naively, well, as x approaches infinity, this term is going to increase without bound. So this is going to approach infinity. And the same thing with x squared. As x approaches infinity, x squared approaches infinity. Well, 1 is just a constant, so it's just going to stay the number 1. And of course, infinity plus 1 is still going to be infinity. So the limit is approaching infinity over infinity. This is called the indeterminate form. It is unacceptable. The indeterminate form really tells you nothing about the limit. So we need some way of avoiding the indeterminate form. We need some way of avoiding infinity over infinity. So I'm going to tell you a trick. The trick is look for the highest exponent in the denominator. That's going to tell you what to divide by. So I'm going to divide each term in this function by x squared. So this should equal the limit as x approaches infinity of 3x squared over x squared. Okay, so I'm dividing the numerator by x squared, But then in the denominator, I'm going to have x squared divided by x squared plus 1 divided by x squared. So I took the three terms in the original function and I divided each one of them by x squared because that was the highest degree in the denominator. Before I go any further, let me just convince you why this was legal. What I really am doing is I am multiplying the numerator and the denominator by 1 over x squared. I'm multiplying the numerator by 1 over x squared, and I'm multiplying the denominator by 1 over x squared. You can see that if I multiply 1 over x squared times 3x squared, that's the same thing as dividing by x squared. And in the denominator, when I do the distributive property, I'm going to wind up dividing each term by x squared. But if you look at it this way, you can see that I'm just multiplying by the same thing over itself. So this is a form of multiplying by 1. So of course that's valid. Multiplying by 1 is not going to change the value of the expression. So this is okay to do. Now let's simplify. So we have the limit as x approaches infinity of, so the x squared will cancel out, and that's going to leave me with a numerator of just 3. X squared divided by x squared is going to be 1. And there's nothing I can do with this, so I'm still going to have 1 over x squared. Let's go ahead and allow x to approach infinity now. Let's find the limit of each term as x approaches infinity in this form. So two of the terms are simply constants, so they will stay a constant. But as x squared approaches infinity, we have 1 divided by a larger and larger and larger number, so that is going to approach 0, right? So hopefully you can see that if I have 1 over x squared, as x squared approaches infinity, okay, we're going to have 1 divided by a bigger and bigger and bigger number. So as you go from 1 divided by 10 to 1 divided by 100 to 1 divided by 100,000, this is getting smaller and smaller and smaller. So any expression like this is going to approach 0. So this is just 3 over 1, which is simply 3. So we have now proven analytically that the limit as x approaches infinity of f of x is equal to 3. Would it make a difference if we did negative infinity? So technically we've only proven half of what we wanted to prove. We've proven that as x increases without bound, the function approaches 3. But what about as x approaches negative infinity? Will that change anything? All right, so imagine that we just change this to negative infinity. Okay, if I just threw this out and I put the limit as x approaches negative infinity, we would go through the same argument, all right, but just now it would be a negative infinity until we get to right here, and it doesn't matter. So as x approaches negative infinity squared, a large negative number, once you square it, it's going to be positive anyway. But regardless, even if it was negative, this would still be approaching 0. So nothing changes. So we can see that the limit as x approaches positive or negative infinity is going to be 3. Please be careful. This is not always the case. Some functions have two different horizontal asymptotes. And for some functions, the limit as x approaches positive infinity is different from the limit as x approaches negative infinity. Let's practice our new skills. Find the limit as x approaches infinity of 2x minus 1 over x plus 1. So first of all, notice what happens if we try to immediately take the limit of the numerator and the denominator. The 2x part approaches infinity, and the minus 1 just stays minus 1. The x, of course, approaches infinity. So this quickly becomes infinity over infinity, the indeterminate form, which tells us absolutely nothing. So that's why we have to use our trick of identifying the highest exponent in the denominator, and that tells us what to divide everything by. So we are going to rewrite this as the limit as x approaches infinity of 2x divided by x minus 1 divided by x over x divided by x plus 1 divided by x. So x itself is the term with the highest power. So I'm dividing each of the 4 terms by x. Now we can simplify and take the limit. So this will be the same as the limit as x approaches infinity of 2, these x's cancel out, minus 1 over x, and this will be 1 plus 1 over x. In this form, we will not get the determinant form as we take the limit. So we're taking the limit of each of these 4 terms separately because of the properties of limits. And of course, the limit of a constant is just that constant. But the limit of 1 over x as x approaches infinity is 0. All right, remember, because if we're dividing by a larger and larger and larger number, the overall value gets smaller and smaller. So we're going to have 1 plus 0. So that's going to give us 2 over 1, which is simply 2. Example 3 says, find the following limits involving rational functions. Remember that a rational function is a function where the numerator and the denominator are both polynomials. So we're going to do this last example as a set of 3 because these 3 examples will lead us to some rules about limits of rational functions that we can use as shortcuts in the future whenever we want to find the limit of a rational function. Let's jump in. For the first one, the highest power of x is 2. So we're going to end up dividing each term by x squared. So this is going to give us the limit as x approaches infinity of 2x over x squared plus 5 over x squared over 3x squared over x squared plus 1 over x squared. Next, we simplify this as far as we can. So we will have the limit as x approaches infinity of, let's see, one of the x's will cancel out, so we will have 2 over x. Nothing we can do with this, so it'll still be 5 over x squared. The x squares cancel each other out, so we will have 3 plus 1 over x squared. Nothing I can do with that. Now that it's simplified, we can go ahead and find the limit. So we'll take the limit of each term separately, and each of these terms that has x in the denominator is going to approach 0 as x gets larger and larger. So we will have 0 plus 0 over 3 plus 0. So that's going to equal 0 over 3 which is simply 0. So that's the limit of the first function. All right, let's take a look at the next one. Well, all of the denominators are the same. So in each case, we are going to end up dividing every term by x squared. So we will have 2x squared over x squared plus 5 over x squared divided by 3x squared over x squared plus 1 over x squared. Simplifying as far as we can, all right, we will get 2 because these cancel out completely, so we are left with 2 plus 5 over x squared and 3 plus 1 over x squared. As before, when we take the limit, these fractions that have a constant in the numerator and x in the denominator, these fractions are going to approach 0 as x gets bigger and bigger. So we're going to end up with 2 plus 0 over 3 plus 0. And that's going to give us 2/3. So that's the limit of this one. Let's look at the final one. Again, dividing each term by x squared, we will have 2x to the third power divided by x squared plus 5 over x squared over 3x squared over x squared plus 1 over x squared. Whoops, I forgot the limit part. So this will equal the limit as x approaches infinity. Okay, so x squared will cancel out 2 of those x's, and that's going to leave me with 2x plus 5 over x squared over 3 plus 1 over x squared. Now we'll take the limit of each term separately like you do. Now, 3 of these we're really familiar with. This one is going to approach 0 because of the x in the denominator. This one is just a constant, so that's going to be a 3. And this one will approach 0 because of the x in the denominator. But 2x, as x gets larger and larger and larger, the expression 2x will just get larger and larger and larger. So this particular term is going to approach infinity. So that means that the function as a whole is going to approach infinity divided by 3, which of course is just infinity. All right, it's going to increase without bound. So in other words, this one has no limit. So let's compare these 3 rational functions to see if we can come up with some rules. We can see that these functions are exactly the same, except the power of the x in the numerator kept changing. So the first one was degree 1, and the second one was degree 2, and the last one was degree 3. That's the only thing that was changing. So the key is this. For the first expression, the degree of the numerator is less than the degree of the denominator, right? Degree 1 versus degree 2. In part B, the degree of the numerator and the degree of the denominator are the same. They're both degree 2. And in the third one, the degree of the numerator is greater than the degree of the denominator. So that's the key. So what happened? When the degree of the numerator was less, we wound up with 0. So that's going to be a rule. That turns out to always happen. Whenever the degree of the numerator is less, the limit as x approaches infinity is going to be 0. And that's the same for negative infinity, by the way. Okay, and don't forget, this means that we have a horizontal asymptote at 0. What happened with the next one? When the degrees were the same, it turned out to be 2 over 3. Where does that show up in the problem? Well, that's just the ratio of the leading coefficients. So whenever the degrees are the same, the limit will simply be the ratio of the leading coefficients. And how about the last one? So when the degree of the numerator is higher, there is no limit. So that's going to be the rule for when the degree of the numerator is higher. So here's a nice summary of the rules for your notes. Go ahead and pause the video and write this down. So the next time we see a rational function, we won't have to divide everything by the highest power of x in the denominator. We can just use these rules as a shortcut.